Okay, so the question is, this is the lab that you guys did, Friday. This is my own data. How much did the speed change by? I want you to give me an answer on your fingers of your hand. 0 meters, it changed by 0 meters per second, by 1 meter per second, by 2 meters per second, by 3 meters per second, 4 or 5. Just with your fingers, all right? And I need everybody to vote. From start to finish, how much did the speed change by? How much did the speed grow? All right, give me a vote with your fingers. All right, what's the answer? It's 1, right? It starts down here at 0 meter per second, and it ends up here at about 1 meter per second. So that's a change of 1 meter per second over this time interval, right? That's how much the speed changed by. So the next thing I want you to look at is how much time did it take for that speed to change? How many seconds? From start to finish. Sorry, let me scroll up just a touch here. From here to here, how many seconds was that? 1 second. So there's this thing we can do. We can say that if I were to do a best fit line from there to there, I could actually calculate a slope of that line, right? And the slope would look something like this. Let me get my stylus for this. The slope of this line would be, I need 2 points, but I already have them. Up here, I've got 1 meter per second at 1 second. And down here, I've got 0 meters per second at 0 seconds. What's the slope of that line come out to be? 1 what? Meter per second per second. All right. The slope of that line is 1 meter per second. What that means is if you look at it, it changed by 1 meter per second in that 1 second, right? If the speed is changing, if the velocity is changing, there's got to be a word for that, right? Does anyone know that word? When speed changes? Starts with an A? Acceleration. It's called acceleration. Acceleration is the slope of this graph. All right? And this thing was accelerating at 1 meter per second every second. I want you guys to do that on your velocity time graph. Give it a best fit line, circle a couple of intersection points, and determine a slope of your of your ball as it rolled down the table. Determine the acceleration. All right, take a few minutes to do that now. Okay, so my toy car accelerated at 1 meter per second per second. Did anyone in the room have a number that was bigger than that? No, okay. So a couple key things. What was the biggest acceleration we had in the room? Did anyone have 0.5 meters per second per second? Okay. Did anyone have more than 0.5? What do you guys have? 0.6 meters per second. So these balls rolling down the ramps were not accelerating quite as quickly. You can't say that the ball went slower or faster because they all started at 0. All you can say is the one that accelerates quicker is the one that speeds up faster. Does that make sense? It has nothing to do with absolute speed. It's has to do with how quickly you can change your speed. All right. So go ahead and we're going to flip over to the notes. So the notes noted, and it's called Acceleration Examples. And I actually have an example of my first car, which I'm very proud of. It's a 1979 Honda Accord CVCC hatchback. Oh yeah, awesome car. Anyone drive an Accord? All right, nice car, right?
Yeah.
It's like pretty much a luxury car. You know, it's not luxury badge, but it's a really well-built car. Well, back in the 70s, the Accords were not quite as nice, but they were still great cars. I love that car. Ran on leaded gasoline, which you tried not to breathe or else it would kill brain cells and give you lead poisoning. Great car. It eventually died because I couldn't get leaded gasoline, so the engine just broke. I tried to fix it myself, but it ended up on my lawn in pieces. My dad was not happy. Anyway, yeah, it was a fun car. It's the kind of car where you could fit a lot of people in as long as they were all 110 pounds or less. Yeah, and it had a heck of an engine in it. You could go like, you'd romp on the gas, you go, and like it had like little squirrels that you could feed carrots to for, on the inside, and then they get going on the hamster wheel. Real fast now. And then the next thing you know, you're at like 35 miles an hour. All right, awesome car. A lot of fun to drive. Belched a lot of like black smoke out the back and out of the engine hood too. So anyway, so what I have here is we looked at acceleration from the point of view of a velocity time graph, and we know that if the velocity changes, that's when you're accelerating, right? But I also wanted to do it from the point of view of a dot diagram or frame by frame picture. So if you look at this dot diagram here, does this diagram show a car that's accelerating? How can you tell? Somebody give me one way to tell that this car is not accelerating. Yeah. Its speed is the same. Yeah. Speed is 10 meters per second the whole time. How else can you tell it's not accelerating? Want to go? No? No other ideas? Look at the spacing. Oh, Tom, you got something? No. Okay, look at the spacing. What do you notice? Yeah, it's every interval is the same interval. Sorry, I'm trying to do this with my fingers. 10 meters per second. 10 meters. 10 meters. 10 meters. Contrast that with the one down here. What do you notice about this one? Is it accelerating? Yeah. What's happening? Speeding up. How do you know? All right? Spacing's getting bigger every time. All right, so there's a couple of ways to look at this. One is to look at the spacing. One is to look at a speedometer. One is to calculate a speed in every interval. 10 meters in 1 second. 10 meters in 1 second. All right, I'm going to scroll down a little bit so you can see. This one actually goes, if you look at it carefully, it goes 4 meters in the first second, then 6 meters in the next second, then 8 meters in the next second, then 10 meters in the next second. How much is it accelerating by every second? Give me a number. 2 meters per second every second. Does that make sense? So that's what I want you to think of when you think of acceleration, is a changing speedometer dial. The fact that the spacing is changing. All right? And lastly, we can also graph the thing. On a position time graph, we get a curve, right? Or on a velocity time graph, the velocity is changing each second. So we have a slope. And guess what the slope of this graph is? 2 meters per second each second. Acceleration is the slope of the velocity graph. All right. You good? Take a few minutes and catch up, and then we'll continue on with the next example. Okay, so here is the next one, example 3. This one, moving forward, accelerating backward. I'm just going to stop for a second. Is it possible to have a negative acceleration? If you did, what would it mean? Yes. Decelerating, what's that? Slowing down. Yeah. So if I was going, if my speedometer said 10 meters per second, then 8, then 6 meters per second, then 4 meters per second, the little needle on the car is moving to the left. Which direction am I traveling? Does a negative acceleration mean I'm moving backward? No, not at all. Right? And this is one of the hardest things to deal with conceptually. When you see a negative sign for acceleration like this is negative 2 meters per second squared, or negative 2 meters per second, it doesn't mean you're going backward. It just means that your velocity is getting less and less and less positive. So you're going from 10 to 8 to 6 to 4. You keep that up, after a while you'll be going backward. But doesn't mean going backward. If you were to graph that out on a position time graph, you actually get this curve. Starts off steep and then curves which way? Positive acceleration meant the position time graph curves up. Negative acceleration means the position time graph curves down. Got it? So you still get the curved graph, but it curves the other way. Curves down instead of up. All right? Velocity time graph starts out with a big velocity and then becomes less and less and less big. Negative 2 meters per second. All right, take a few minutes and get that one down. Okay, so everybody, any questions on example 3? All right. So, last question I have for you. What does a negative acceleration mean? Does it mean you're slowing down? Or does it mean something else? All right. Last question. Moving backward, slowing down. I actually want to change some of the numbers on here. All right, because I made a mistake. I'm going to cross out some of these. And change this to, yeah. So instead of 10, 50, 30, 20, I want you to change it to 10, 50, 20, 10. I already have it changed on my screen. 10, 50, 30, oh, sorry, 20, 10. So these two numbers right here, change them to 20 and 10. All right. So what we have here, so we have a car that starts off over here on the right. And which way is it moving? Backward. All right? That first second, how far does it travel? How many meters? From here to here, how far is that? That's 50 meters in the first second. Then from here to here, how many meters? 30 meters. And then 10 meters. So we can say, if we actually put the numbers on it, it's negative 50 meters per second, negative 30 meters per second, and then at negative 10 meters per second. How much is it changing by each second? If it goes negative 50, negative 30, negative 10. What's the acceleration? How much? Give me a number. All right, I'm going to pause it here and let you guys... Yeah, we got this really weird effect here. You've got this positive 20 acceleration because of the way these numbers work. Moving backward, slowing down means positive acceleration. So what would that look like if I were running? Well, I'd start over here, and I would run like this. You ready? Try to do this without breaking anything. All right, here we go. And slowing down. That was positive acceleration. I was going backward, slowing down. Got it? All right. Okay, graphs. Hey, look at this curve. I do have a curved graph again, but it's becoming less steep negative. It's kind of curving up. And look at the velocity graph. It starts off big negative, and it points in the positive direction with a positive slope. All right? Positive acceleration, you should know it from the slope of the velocity graph is positive. Curves up on the position graph. Less and less negative velocities. All right, is this a positive or negative acceleration? It's positive. All right. And that's it. This one right here, this example 4, is, I would say, the most difficult one to learn. All right? So what I want you to do now is take a look, finish up the back page of your lab. And oh, by the way, notice that if you go to 2 pages down in your notes, I put together a cheat sheet. All right, go ahead, finish your labs. You have the cheat sheet, and get them in by the end of the day.